Now the next topic that is the dipole in a uniform magnetic field. Same in electrostatics also we discussed the electric dipole in uniform electric field. Now here we have to discuss the magnetic dipole in the uniform magnetic field. So when magnetic dipole is placed in the uniform magnetic field, so dipole means bar magnet, two poles are there, one is north, another one is south pole. Okay. So if it is placed at some angle with the magnetic field, then in the magnetic field, north pole and south pole will experience the forces in mutually opposite directions. In mutually opposite directions. And this couple means these two forces will equal in magnitude, opposite in direction, and not collinear, will produce the torque. So here the torque acts on the dipole when it is placed in the uniform magnetic field. So if it is at some angle theta, then torque acts on it, that is tau, that is equal to magnetic moment M cross magnetic field B. Magnitude wise torque, that is MB sine theta. Now under the effect of this particular torque, dipole will be rotated in such a way that theta decreases. It implies that we can say this thing here, the torque produced will rotate the dipole in the opposite direction of theta. And therefore here we have to introduce one negative sign. Okay. So under the effect of this torque, it will rotate so that theta decreases. Therefore, tau, that is minus mb sine theta. Now, if we take theta that is very small, then sine theta that is nearly equal to theta. So we can write tau that is equal to minus mb theta. Now in standard 11th, we studied this thing. Torque tau that is equal to I alpha, where I that is the moment of inertia, alpha that is the angular acceleration. So we can write torque tau that is I alpha that is equal to minus mb theta. But alpha, the angular acceleration, that is 2 time differentiation of angular displacement with respect to time t. So we can write I d2 theta by dt2 that is equal to minus mb theta. Now take I on right hand side, so we can write d2 theta by dt2 that is equal to minus mb upon I into theta. Now we can say this one is the differential equation for the motion of this bar magnet or magnetic dipole in uniform magnetic field. Now see, the form of this particular equation, that is exactly like the equation, differential equation of simple harmonic motion. The differential equation for the simple harmonic motion, that is d2y by dt2 equal to minus omega square y. So here from comparison of these two equations, we can say this thing: if dipole is placed at some angle with magnetic field, and then if we release it, then dipole will execute simple harmonic motion, or we can say it will execute simple harmonic oscillations. Now, here if we compare these constants of the motion, then we can write omega square, that is equal to mb upon I. Therefore, omega, that is under root mb upon I. So this is the angular frequency for the simple harmonic oscillations of magnetic dipole in uniform magnetic field. Now, omega, that is 2 pi f, and that is equal to under root mb upon I. So we can write frequency of the oscillations f, that is 1 upon 2 pi under root mb upon I. So from this one, we can write the periodic time for the oscillation of the dipole, that is 2 pi under root I upon mb, because periodic time, that is 1 upon frequency. Clear to all of you? Now see, in standard 11th, we studied about work done under the effect of variable force. And that is integration fx dx, where f is a function of x. Here, torque is a function of theta. So torque is the variable one. So under the effect of variable torque, the work done to rotate the dipole by angle theta, that is how much. So we can write the equation for the work done to rotate dipole by angle theta, that is W equal to integration tau theta d theta. But tau, that is mb sine theta. So integration mb sine theta d theta. And this work done will be stored in it in the form of potential energy. So we can say this work done, that is the magnetic potential energy of the dipole. And now integration of sine theta, that is minus cos theta, mb is constant, so keep it as it is. Okay. So we can write the equation for the magnetic potential energy of the dipole, that is minus mb cos theta. Or you can write the potential energy, that is minus m dot b. Now here we can discuss two special cases. If we take theta, that is equal to 0, then cos theta, that is cos 0. So here magnetic potential energy, that is minus mb cos 0, that is equal to minus mb. And this one is the minimum potential energy. So when the dipole is aligned with the field, at that time, its potential energy, that is minimum one, and that is equal to minus mb. And this particular position of the dipole, that is called stable equilibrium. That is called stable equilibrium. Now, if we take theta, that is equal to pi, then the potential energy, that is minus mb cos pi. Cos pi, that is minus 1. So we will get cos pi minus 1 into minus mb, that is plus mb. That is the maximum potential energy. And the dipole moment is exactly in the opposite direction of the external field. So it is called unstable equilibrium. The same type of theory we discussed for electric dipole also. Clear to all of you? Now example 5.1. The magnetic needle has magnetic moment 6.7 into 10 raised to minus 2 ampere meter square and moment of inertia I, that is 7.5 into 10 raised to minus 6 kilogram meter square. It performs 10 complete oscillations in 6.7 seconds. What is the magnitude of the magnetic field? Now see the magnetic moment given to you, that is 6.7 into 10 raised to minus 2 ampere meter square. I, moment of inertia, that is 7.5 into 10 raised to minus 6 kilogram meter square. Now 10 oscillations are completed in 6.7 seconds. It implies that time for one oscillation, that is 6.7 by 10, that is 0.67 seconds. And we want to find the magnitude of magnetic field. Okay. So we have the equation for the periodic time, that is equal to 2 pi under root I upon mb. Therefore, T square, that is 4 pi square I upon mb. Now make b as a subject of equation. So we can write b, that is equal to 4 pi square I upon mt square. So substitute the values. 4 pi, that is 3.14 square of it. I, the moment of inertia, 7.5 into 10 raised to minus 6 upon magnetic moment m, that is 6.7 into 10 raised to minus 2, and t, that is 0.67 whole square. Now solve this one, you will get the answer 0.01 Tesla. Clear to all of you? Example 5.2. A short bar magnet placed with its axis at 30° with an external field of 800 Gauss experiences a torque of 0.016 Newton meter. What is the magnetic moment of the magnet? B. What is the work done in moving it from its most stable to most unstable position? C. The bar magnet is replaced by a solenoid of cross-sectional area 2 into 10 raised to minus 4 meters square and 1000 tons, but of the same magnetic moment. Then determine the current flowing through the solenoid. Now see the information given to you, that is the magnet is placed at 30° with magnetic field of 800 Gauss. So 800 into 10 raised to minus 4 Tesla. So that is 8 into 10 raised to minus 2 Tesla. Torque that is given to you 0.016 Newton meter. First, we want to calculate magnetic moment of the magnet. Now we have the equation for the torque, tau, that is mb sine theta. Magnetic moment m, that is equal to tau upon b sine theta. So tau, that is 0.016, b, that is 8 into 10 raised to minus 2, sine theta, that is sine 30. So if you solve this one, your answer will be 0.4 ampere meter square. Clear up to this one? Now question B, we have to calculate the work done to rotate it from most stable to most unstable position. So see, W, that is change in energy, U2 minus U1. So W, that is U for theta equal to pi, that is most unstable final position, minus U for theta equal to 0, that is initial position, most stable one. So the equation for U, that is minus mb cos theta. So for most unstable position, theta, that is pi. So minus mb cos pi, then minus mb cos 0. So here we will get plus 2mb, 2m, that is 0.4 we calculated here. B, that is given to you 8 into 10 raised to minus 2. Now solve this one. You will get the answer 0.064 joule. Clear to all of you? Now question C. We have the solenoid. Which one is with cross-sectional area 2 into 10 raised to minus 4 meters square? Number of turns in it, that is 1000. And magnetic moment of this solenoid, that is exactly equal to the magnetic moment of that bar magnet. So if we replace that magnet by this solenoid, then what should be the current in the solenoid? So magnetic moment of the solenoid, that we can write as NIA, but that is equal to magnetic moment of bar magnet. Now we want to calculate the current. So current I, that is equal to M upon NA. M we calculated 0.4 and the number of turns given to you 1000, and area A, that is 2 into 10 raised to minus 4. Solve this one, you will get the answer 2 ampere. Clear? Now example 5.3. A. What happens if a bar magnet is cut into two pieces transverse to its length along its length? In both the cases, you will get two magnets, each that is with north pole, south pole, and their strength will decrease. Question B. A magnetized needle in a uniform magnetic field experiences a torque but no net force. An iron nail near a bar magnet, however, experiences a force of attraction in addition to torque. Why? Because the magnetic field of the bar magnet, that is non-uniform one. So in non-uniform magnetic field, if the magnetic moment is there, then it will experience the torque and force both. C. Must every magnetic configuration have a north pole and a south pole? What about the field due to toroid? It is not necessary. Each magnetic configuration must have north-south poles, because we know this thing. For toroid, it is endless. Okay, so we can consider it as an infinite one. So in that, north pole, south poles are not there. Okay, so only if the source of the field has a net non-zero magnetic moment, then and then only north-south pole will be there. Otherwise, not. Clear up to this one? D. Two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. We do not know which one. How would one ascertain whether or not both are magnetized? If only one is magnetized, how does one ascertain which one? Use nothing else but the bars A and B. So see here what we have to do. Suppose we have these two bars. One is magnetized, another one is not. Then how one can understand this thing? Only one is magnetized. So see, we have to place these two bars like this. Okay. And then after like this. So if repulsive force is experienced between these two in either of these case, then we can say both are magnetized one. But suppose in this situation attractive force is there, in this situation also attractive force is there, it implies that one bar is normal bar, another one that is the magnetized one. So in this way, one can understand this thing, both are not magnetized one. But then after, out of these two, which one is magnetized and which one is not magnetized? So the bar which one is magnetized, for that, the field strength that will be more at the end and less at the center. So suppose we place this particular another bar at this end, and suppose it experience strong force. Here also it experience strong force. But at the center, if we place this one and this experience weak force, it implies that this one is magnetized one and this one is normal bar. Suppose this one is placed here, here, and here. In all these three positions, the force between these two, that is the same one, then in that case, this upper one is magnetized one and this one is normal bar. Clear to all of you? So in this way, one can understand which one is magnetized one, which one is not magnetized one. Clear to all of you? Now the next topic, that is electrostatic analog. So there is the analogy between the electrostatic and magnetics. Okay. Now see here how one can understand this analogy. So quantities in electrostatics and magnetics. So analogy means the role of the respective physical quantities in respective branches, that is the same one, that is the analogy. Okay. So constant quantity in electrostatic, that is 1 upon 4 pi epsilon 0, where epsilon 0 is permittivity of free space, and charge q. These are the constants of electrostatics. In magnetics, the constant that is mu 0 upon 4 pi, where mu 0 that is the permeability of free space. Okay, and P that is pole strength. Here one more thing that you have to keep in your mind, the role of positive charge in electrostatic and role of north pole in magnetics, that is identical one. Similarly, in electrostatic, the role of negative charge, and in magnetics, role of south pole, that is identical one. Then dipole moment in electrostatics, that is given by P equal to Q into 2A. And in magnetics, it is given by M, that is equal to here P into 2L. Asudari karjo. Pole strength P into 2L. Now in electrostatics, 2A, that is the distance between two charges, positive and negative. And in magnetics, 2L, that is the distance between two poles, North Pole and South Pole. And dipole moment, that is represented in the direction from negative charge to positive charge. And here in magnetics, the magnetic dipole moment, that is represented in the direction from South Pole to North Pole. Then equatorial field for electric dipole, that is EY equal to minus 1 upon 4 pi epsilon 0 P upon Y square plus A square raised to 3 by 2. Then if we take Y, that is very much greater than A, then 1 upon 4 pi epsilon 0 P upon Y cube. Similarly, equatorial field for magnetic dipole minus mu 0 upon 4 pi C, the constant is replaced by constant. Then M, dipole moment. This is dipole moment. Then Y square plus A square. So here A is replaced by L. So Y square plus L square raised to 3 by 2. If we take Y, that is very much greater than L, then we can write mu 0 upon 4 pi M upon Y cube. Then axial field, electric field for electric dipole on its axis, that is 1 upon 4 pi epsilon 0 2p z upon z square minus a square whole square. Similarly, for magnetic dipole, the magnetic field on the axis mu 0 upon 4 pi 2m z upon z square minus L square whole square. If we take Z, that is very much greater than A, then electric field, that is 1 upon 4 pi epsilon 0 2p upon Z cube. And if we take Z, that is very much greater than L, then magnetic field on the axis of the magnetic dipole, that is mu 0 upon 4 pi 2m upon Z cube. Clear up to this one? Now, when any charge Q is placed in the electric field E, the force acts on it, that is Q into E. Similarly, when any pole having pole strength P is placed in the magnetic field B, the force acts on it, that is P into B. Now, when electric dipole is placed in the external electric field, the torque acts on it, that is P cross E. Similarly, when magnetic dipole is placed in external magnetic field, the torque acts on it, that is M cross B. Then, when electric dipole is placed at some angle in the external electric field, then the potential energy of it, that is minus P dot E. Similarly, when magnetic dipole is placed in the external magnetic field, its potential energy, that is given by minus M in dot B. So from this analogy also, you can easily write the equations for electrostatics and magnetics. Clear to all of you? Example 5.4. What is the magnitude of the equatorial and axial field due to a bar magnet of length 5 centimeter at a distance of 50 centimeter from its midpoint? The magnetic moment of the bar magnet is 0.4 ampere meter square. Very simple example. See, R the distance, R that is the distance from the center of the bar magnet, that is 50 centimeter, 0.5 meter. Then magnetic moment, that is 0.4 ampere meter square. Now, equatorial field. So B equatorial, that is mu 0 upon 4 pi M upon R cube. mu 0 upon 4 pi, that is 10 raised to minus 7, m that is 0.4, r that is 0.5, cube of it, solve it, you will get the answer 3.2 into 10 raised to minus 7 Tesla. Then axial field, so that is mu 0 upon 4 pi 2m upon r cube. But for the same position, if r is the same one, then simply we can write mu 0 upon 4 pi m upon r cube, that is B equatorial. So at the same distance on the axis, the field that is double than that on the equator. So 2 times B equatorial. So B equatorial we calculated. Multiply this one by 2. So your answer will be 6.4 into 10 raised to minus 7 Tesla. Clear? Example 5.5. Figure shows a small magnetized needle P placed at a point O. The arrow shows the direction of its magnetic moment. The other arrow shows different positions and orientations of the magnetic moment of another identical magnetized needle Q. A. In which configuration the system is not in equilibrium? B. In which configuration is the system in 1. Stable and 2. Unstable equilibrium? C. Which configuration correspond to the lowest potential energy among all the configurations shown? See here, one dipole that is P, another dipole Q is placed at 6 different positions, Q1, Q2, Q3, Q4, Q5 and Q6. Now, for this particular arrangement, we have to give these answers. Clear the question? Now, here we can say this thing, the dipole Q, or we can say magnetized needle Q, is placed at different positions in the magnetic field of magnetized needle P. Now, magnetic field of magnetized needle P, that we can write as on the axis mu 0 upon 4 pi 2 mp upon r cube. So this field will be in the direction of magnetic moment of P. B equatorial, that is minus mu 0 upon 4 pi mp upon r cube. This negative sign represent this thing, the field at any point on the equator that is in the opposite direction of magnetic moment. Clear to all of you? Now see the figure. The magnetized needle P that is placed at O and dipole moment that is represented in upward direction here. Okay. Now see here PQ1, this one, and PQ2 are not in equilibrium because the magnetic field on the equatorial line, this is the equatorial line for P. So magnetic field of P at any point in the equatorial plane, that is vertically downward. जो equation प्रमाणे in the opposite direction of MP. So magnetic moment that is this direction. So on the equatorial line, it is downward. So here the magnetized needle Q and the magnetic field of P both are perpendicular for the position Q1 and Q2, and therefore we can say these two positions are not in equilibrium. Clear this thing? For most stable equilibrium, the dipole moment that should be in the direction of the magnetic field, and for most unstable position, the dipole moment and magnetic field should be in opposite direction. Now see, think about Q3. So when the magnetic needle Q that is in the position Q3, so it is on the equator of the P, so magnetic field of P that is also vertically downward, Q3 that is also downward. It implies that the angle between the magnetic field of P and magnetic moment of Q, that is 0. Therefore, we can say it is most stable position. Clear this one? Now, magnetic field of P on its axis, that is in the direction of the magnetic moment, and magnetic needle Q that is placed on the axis but in the opposite direction of the magnetic field of P. So theta, that is pi in this case, so we can say this particular position that is most unstable. Clear to all of you? Then after magnetic needle Q is placed in position Q5, and here for magnetic needle Q, the magnetic moment that is upward, but it is on the equatorial line of P, and magnetic field of P on the equator that is downward is in opposite direction of the magnetic moment of P. So magnetic moment of Q that is upward, magnetic field of B that is downward. So the angle between those two, that is pi. So we can say this position Q5 that is also most unstable. Clear? Now Q is placed at position Q6. Its magnetic moment that is in the direction of the magnetic field of P, magnetic field of P that is along the axis that is in the direction of magnetic moment of P. So here the magnetic moment of Q and magnetic field of P both are in the same direction. So theta that is 0. So we can say this particular position that is also most stable position. Clear to all of you? Then after magnetism and Gauss's law. Now Gauss's law for magnetism suggests this thing: the net magnetic flux through any closed surface that is 0. See, suppose here we consider any closed surface in the magnetic field. And now if we consider infinitesimal small surface element here, that is ith element, for which the area vector that is delta Si, and suppose the uniform magnetic field at this particular surface element that is Bi. Then magnetic flux passing through this ith surface element that is Bi dot delta Si exactly like we discussed the electric flux, that is E dot delta A. So if we want to calculate the total flux passing through this particular closed surface, then we have to divide this entire surface into this type of so many infinitesimal small elements. Then we have to calculate the flux passing through each one. Then we have to take the summation of all those, and that will be the algebraic summation. So we can write the resultant flux phi, that is sigma I equal to 1 to n phi I. So we can write sigma I equal to 1 to n bi dot delta si. Now here if we take limit delta s tends to 0, then this summation that we can represent by integration. So flux passing through any surface that we can calculate as integration b dot ds. Clear up to this? Now as per Gauss's law, we can write the flux passing through closed surface, that is equal to 0. Now see here, for electric flux, we discussed this thing, the electric flux passing through any closed surface, that is equal to sigma q upon epsilon 0, where sigma q, that is the net charge enclosed by that closed surface. Suppose here exactly like this one, we write the Gauss's law for magnetism. Then integration over the closed surface of magnetic field. So integration b dot ds over the closed surface, that is equal to, now constant in magnetics here 1 upon epsilon 0 for electrostatic, that is replaced by mu 0. Then this is electric charge, this is magnetic charge. So sigma qm. But as per Gauss's law, this flux passing through closed surface is always 0. It implies that here on right hand side, this sigma qm must be 0. So when sigma qm, that is always 0, it implies that the independent magnetic charge means independent magnetic pole is not available in the nature. So we can say monopole does not exist in the nature. That we can conclude from the Gauss's law. Clear to all of you?